Hello Rian, here is my video for numerical integration, and we'll be going over the trapezium and the Simpson's rule. So firstly, the trapezium rule. So generally, if we're taking the area, so these are defined areas underneath the curve, but they're approximations, so they're going to be slightly inaccurate, and we're going to show you why it's inaccurate. So the first one is trapezium rule. So say that we're taking the area from two different points. So it'll be x0 to xn. So this is a slightly different notation to what we're used to. This just means the x0 just means the first x value, and then xn is the last x value. And then you're taking that of a function of x dx, and the trapezium rule expands out to give you the area is equal to half times h, and I'll explain what that means later, multiplied by y of 0 plus y of n plus 2 times y of 1 plus y of 2, and so on until you get to y of n minus 1. So what do these values mean? So the h is the regular interval between trapeziums, or between the x values, and y of 0 is the first y value, and then y of n is the last y value, and then everything in between, y of 1, 2, 3, 4, and so on until you get to n minus 1 is the y values in between of this function f of x. And you calculate the regular interval. Sometimes they'll give it to you, but if they don't give it to you, you can choose how many intervals you would like, but the average interval distance is equal to the last value of x minus the initial value of x divided by the number of intervals, or the number of gaps you wish to have. You can choose any number. So, what does this look like graphically? So say you've got this arbitrary curve, and you wish to find the area between this x value and this x value. So, to the left, that is the first x value, x0, and then to the right is the last value, x of n. And say you wish to split this into 4 trapeziums. So you'd want to divide this in half, and then divide those halves into halves again. So you've divided it into 4 regions. So, at x of 0, and this equals x of 1, x of 2, x of 3, and so on, until you get to x of n, which is x of 4, because you chose to divide it into 4 regions. Now, at each of the x values, there's going to be a corresponding y value. So this is going to be y of 0, y of 1, y of 2, y of 3, and y of 4. And that describes the height of the trapezium. Now, if you join the two ends of the trapeziums together, you'll get shapes that look like this. So drawn like that, to there, and to there. Now you'll notice that it's slightly inaccurate. Like for example, the first trapezium, there is missing area over there, where the trapezium doesn't account for. So that's where your source of inaccuracies are when you're using the trapezium rule or any other numerical integration. And then the gap between the x values is known as your h value. You can calculate your h value by using this expression up here. So that's what it looks like visually. Now let's use an example question. Calculate, using the trapezium rule, the approximate area under the curve, y equals square root 2x plus 1 from x equals 0 to x equals 1. So just initially, using the trapezium rule, so you know that the area is going to be half of the average gap distance multiplied by the first y value plus the last y value plus 2 times all of the other y values. Like so. So what you need to do is you need to find the regular interval distance. You need to find your y values of this curve. So we know that we're going from x equals 0 to x equals 1. So we can choose to, let's say, divide this into 4 regions. If we divide it into 4 regions, we'll get, we can calculate h as x, the last value of x, minus the first value of x, divided by the number of gaps that we want. And if we choose 4, we have 1 minus 0 divided by 4, which is 1/4, or 0.25. So the average interval distance is going to be 0.25, which means that if we draw a table of x values and the corresponding y values, which is square root of 2x plus 1, by the way, like so, the first value of x is going to be at 0, and the next value is going to be at 0.25, and then 0.5, 0.75, and then 1. Because we chose to divide it into 4 regions, so each region will have a difference of 0.25, and so you plug these x values into your y equation, and you'll get the following results. Y is equal to 1, 1.22, 1.41, 1.51, or 58, sorry, and then 1.73. So, at x equals 0, this is your first x value. X equals 1, that is your last x value, xn, or x of 4. So, your corresponding y values of 1 is going to be y of 0, and this one being y of 4. Everything in between is going to be 1, 2, 3, 1, 2, 3. So then what does this look like for the area equation? So using all these values now and substituting them into the area equation, you'll now have area is equal to half times the average interval distance of 0.25 multiplied by the first y value, which is 1, plus the last y value, which is 1.73, plus 2 times all of the y values in between. So it'll be plus 1.22, plus 1.41, plus 1.58, and all of that gives you a final answer of 1.3938. So that is your approximate area with using the Trapezium rule. Okay, now let's move on to Simpson's rule. Simpson's rule is very similar to the Trapezium rule in that it's still a numerical integration, and it kind of also draws the same trapeziums that you see in the Trapezium rule, but just uses a slightly different form. So, the general formula for this, again, is you're taking the integral, the definite integral from an initial x value to the final x value, x of n, of a function, and that will give you delta x over 3 multiplied by y of 0 plus 4 times y of 1 plus 2 times y of 2 plus 4 times y of 3, and so on, plus 4 times y of n minus 1 plus y of n. That might look a little bit terrifying, but what you need to know here is that there's a 4 times the y value of an odd number, and then 2 times the y value of an even number. So you can rewrite this expression as delta x over 3 times y of 0 plus y of n, so those don't have any coefficients from them, plus 4 times the sum of all the odd y values plus 2 times the sum of all of the even y values. This is a much simpler way of expressing it that doesn't involve 4s and 2s everywhere for every y value that you have. So what do these values mean? So all of the y values is exactly the same as what you saw in the previous one with the Trapezium rule, but now we've got this delta x over here, which is the exact same as h. It's still the regular interval distance, however it's calculated similar with one minor tweak. So delta x is equal to x of n minus x of 0 divided by n, which is the same thing that we saw before. However, n has to be even. It has to be an even number. So just make sure when you're doing the Simpsons rule that the number of intervals that you have is an even number of intervals. So let's look at the exact same question. This should say Simpson's rule. Sorry, my bad. Let's say we're using the Simpson's rule, but for the exact same question. Calculating the area under the curve of y equals square root 2x plus 1 from x equals 0 to x equals 1. So, we can do the exact same thing we did before and divide into 4 regions, so we can let n equal 4, because this is an even amount of gaps in between. And so, delta x is going to equal to x, the last value of x, minus the first value of x, divided by n, so it's going to be 1 minus 0 divided by 4, which still gives you a gap of 0.25. So again, you need to find all of the y values for the corresponding x values from 0 to 1. So again, you're drawing your table from x and then y, which is square root 2x plus 1, which you're going to construct the exact same table as before. So at x equals 0, and then the next interval will be at 0.25, next one at 0.5, next one at 0.75, and 1, which gives you the exact same values: 1, 1.22, 1.41, 1.58, and 1.73. Again, your corresponding values, this is x of 0, y of 0, and because there are 4 regions, the last one's going to be x of 4, and then y of 4, and then everything in between is going to be x of 1, 2, and 3. So this is odd, even, odd. Now you're only concerned about the odds and evens for the x and y values on the inside. The first and last values, they don't have a coefficient in front of them, so we're not concerned about whether or not it's even or odd. So then we can use our area equation of Simpson's rule, being delta x over 3 multiplied by the first y value plus the last y value plus 4 times the sum of all of the odd y values plus 2 times the sum of all of the even y values. So delta x, as we explained before, is equal to 0.25 because we chose to divide into 4 equal regions, and it's an even number, so it works out, divided by 3, multiplied by the first y value, which is 1, plus the last y value, which is 1.73, plus 4 times the sum of all of the odd numbers. So the odd numbers is going to be 1.22 plus 1.58, that's all of the odd numbers, plus 2 times the sum of all of the even y numbers, which is 1.41 only. So then use your calculator again to just solve all of this, and you get an answer of 1.3958. Now, look at the difference between the values. Before, we're using Trapezium Rule, 1.3938, now it's 1.3958. They don't agree with each other, but because they're both numerical integrations, they're both approximations, so they're never going to be that accurate. So let's show that both of them are inaccurate. So we need to show that both of them are not accurate by taking the regular interval. So we're going to take the definite integral of the area between 0 to 1 of square root 2x plus 1 dx, which you can do using chain rule. So 0 to 1 of 2x plus 1 to the power of 1/2 dx. So I'll give you the area equal to, well, 2x plus 1 is the inside function that stays the same. Add 1 to the power, 3 over 2, divided by the new power. So dividing by 3 over 2 means you're multiplying by 2 over 3, but then you also need to divide it by the derivative of the inside, so it's divided by 2. So these two cancel each other out. And we know that we're taking it from 0 to 1. So this is 2x plus 1 to the power of 3 over 2 divided by 3 between 0 to 1. So that will be 2 times 1 plus 1 to the power of 3 over 2 over 3 minus 2 times 0 plus 1 to the power of 3 over 2 over 3. And in your calculator, you should get 1.399. So this proves that you're taking the definite integral, so you're not using a numerical integration, it's not drawing shapes, but it proves that both of them are inaccurate. So those are your limitations there. So it's good because, it's not very difficult to calculate the area, give an approximation, because you're just drawing shapes and filling in these numbers over here. But the limitations for using these numerical integrations is that they're not accurate and they won't give you the right answer. So let's look at an NCEA example. So this is 2021 question 3b. It's worth achieved, which is somewhat why I don't want to go through too much numerical integration with you, because they're only worth achieved, at most more. So let's see here. Use the values given in the table below to find an approximation to the integral from 1 to 2.5 of the function using the Trapezium rule. The Trapezium rule we're going to recite is the area is equal to 1/2 times the regular interval distance of times the first y value plus the last y value plus 2 times all of the other y values. So what we need to find out is the y values, all of them, and then also the regular interval distance, which is calculated by h equals the last value of x minus the first value of x divided by the number of intervals. Now, this is not necessary because you can see that the regular interval distance between the x values is always 0.25. So here you can immediately say that h is equal to 0.25. There's no need to calculate that. It's already been given to you. And then they've also given you all of the y values associated with the x values. So remember that the start is x of 0 and the end is x of n. So the area is given by 1/2 times the regular interval distance, which is 0.25, multiplied by the initial y value, or f value, which is 0.8, plus the last y value, which is 2.4, plus 2 times all of the intermediate y values, or everything in between. So it's 1.1 plus 1.5 plus 1.9 plus 2.2 plus 2.1. Right, so that's ignoring the first and last values. And if you put this in your calculator, you'll just get 2.6. And that's it. That's all they want from this question. Now let's move on to the next one. So from 2023, question 3a, also worth achieved. A garden designer wants to find an approximation of the area of a section of a garden shaded below. They take some measurements, and these are shown in the diagram. Okay, cool. Using these measurements and Simpson's rule, find an approximation of the area of the garden section. So let's recite the Simpson's rule. So that is going to be the average interval distance divided by 3 multiplied by the first y value plus the last y value plus 4 times the sum of the odd y values plus 2 times the sum of the even y values. So let's look at what this context is. So imagine this is the x-axis and then this is the y-axis. You can see that the average distance between each of these sections is 3. So the change in the x, the average interval distance, is going to be 3. So let's write that in here. Oops. Delta x equals 3. That's the average interval distance. And then they've given you measurements like so. And so you know that this is the start of the measurements. So that's the start of the integral. And this is the last measurement. So that's the last measurement of x. So this is going to be x of 0, and this is going to be x of n. Now we're going to count how many regions do we have. We've got 1, 2, 3, 4 regions here. And so this is going to be x of 1, x of 2, x of 3, and then x of n is actually equal to x of 4. So there are going to be corresponding y values. So this height is going to be y of 0, y of 1, y of 2, y of 3, and then y of 4. So let's put all of this information into the area equation, the Simpson's rule. So delta x is going to be 3, because the average interval distance is 3, divided by 3, multiplied by the first y value, so the first measurement is 10, plus the last y value, which is 14, plus 4 times the sum of all the odd y values. The odd one is y of 1, and then y of 3. So that's going to be 13 meters, plus 15 meters, and then plus 2 times the sum of all of the even y values, which is y of 2 here. So that is going to be 16 meters over there. And if you put that in your calculator, you'll get an answer of 168. And that's it. Now this is good because we've got 4 regions, 1, 2, 3, 4. So it satisfies the requirement that the number of separations or the number of intervals is even. So just make sure it's always even before you do the rule, which I should have started off with. And yeah, that's worth achieving. So I hope this helps. You can go through the EAS book and some of the past questions if you wish, but I won't spend too much time on this because it is never worth that much in an exam. But I hope this helps. Yeah, and that's all.